Next up is Gibbs free energy. And we're going to continue to look at Gibbs free energy in the context of a system in which the piece that we're really interested in, A over here, is really small compared to the rest of it. And this is useful in the context of what we're thinking about in terms of biological systems, because this could be a cell with respect to the rest of the body, all kinds of things that where this reservoir out here, yeah, this cell's not really going to change the rest, right? So Gibbs free energy by definition is the energy minus the temperature over here times the entropy over there plus the pressure over here times the volume over there. That's it by definition. And if A prime is large enough, then we're not changing that temperature T. We're not changing the pressure over there. So when we take the derivative of G, we just get dG is du minus T prime ds plus P prime dV. Remember, the prime is over in the big reservoir, and the other variables are over in a little bitty bit, which gives us ds star, which is the overall entropy of the system, is minus dG over the T prime, the temperature of the reservoir. So the change in entropy of a system plus reservoir is related to the change of G, which is a property of the system. And as long as the pressure and temperature are maintained constant by the reservoir, right? So as always, there are caveats. Well, let's look at Gibbs free energy in another context. Consider we've got dW is minus du plus TdS, which is really just saying, change in energy is Q minus W. We're back to the fundamental property uh, of the beginning of thermodynamics, right? If we subtract PdV from both sides, work minus PdV is minus dG, right? So we have minus dG on one side. We have change in work minus PdV on the other side. What does this mean? Well, PDV is also a work, right? It is a kind of work. Pressure moving through volume is work. And so this means that work done in any isothermal, isobaric, so constant temperature, constant pressure, reversible process, exclusive, and that means minus, the PDV work is equal to the decrease in Gibbs free energy. Right? So keep in mind, whenever we're talking about thermodynamics, you have to keep straight what are the special conditions under which we're operating. All right, consider a reaction, right? So this is like oxygen, hydrogen, and you got your reaction going on here, and so we've got G is U minus TS minus PV, and so when we take the derivative, dG is du minus TdS minus S dt plus PdV plus VdP. That's the complete derivative of that. Since it's a constant temp and pressure, dP and dt are 0. All right, and then we grab equation 3.60 from the book, and we get TdS is minus all of this stuff, right? Well, we write that in terms of dG. dG, right? dG is in this. dG is minus the chemical potential of A times the change in number of A's. Plus the chemical potential of B times the change in number of B's plus chemical potential of C, etc. We know the concentration dependence of the chemical potential, right? So we know the concentration goes as your reference concentrate, your default chemical potential for a reference concentration plus kBT log of your concentration over reference concentration. And if we choose the same reference concentration for everything, which we do, as 1 mole per liter, then these different dNs work out to be minus A dN overall N minus B dN, right? So you get a minus sign over here, you get a plus sign over here, and so that gets us to a new way to write dG with lots of different terms. We're eventually going to get rid of some of this, lots of different terms. But we've got one and only one dN. right? A very useful thing to get it down to a um, single variable over here. So we've got the number of C's we have times the chemical potential of C at the reference concentration, etc., plus KBT onto this ratio of concentrations. And if you're wondering where these came from, right? Well, these are log terms out here. And so when you multiply A times log, that's log of C to the A, right? And so that's where those came from. And we've made the notation change that CA is A in brackets, right? So these multipliers, these A's, B's, and C's, and D's end up there as an exponent from the property of logarithms. So if we take this, we multiply by Avogadro's number, that changes to the Gibbs free energy per mole, and this KB changes to R, and here we go, and change in moles instead of change in number of particles. A little bit more useful in this, in that you don't usually spend a lot of time counting the number of oxygen particles. So Gibbs free energy in chemical reactions. Standard free energy of change, delta G0, which is defined by, you've seen this before in chemistry, right? Your Gibbs free energy of each, molar Gibbs free energy of each constituent in the reaction. And if we're at equilibrium, delta G is 0. So if at equilibrium back here, that's 0, we're just left with that side of the equation. And this lets us calculate, well, when are we going to be at equilibrium, right? We're going to be at the equilibrium when the equilibrium constant is this. So we're going to be at equilibrium when our change in the standard free energy equals minus RT times the log of K equivalent, our equilibrium constant, right? Cool. We figured out how to know where we're going to end up in terms of the equilibrium. Now we got to just be able to write the concentrations in terms of something that we can relate to each other so that we can evaluate this, right? Chemical potential of a solution, mix a solute with a solvent. And here we by default say water is the solvent. It could be some other solvent. Total amount of particles is N is the number of solute particles plus the number of water particles. And this gives us the number of available microstates, right? Just from the factorials. So the change in entropy of a solution minus solution of the entropy of the solution minus entry of pure water and pure solute, right? That change in entropy is just Kb on the log of the number of microstates the solution has, divided by the number of microstates in the pure state. Well, number of microstates of the solution minus number of microstates in pure, right? We end up with this term. Since the n's are extremely large, we're going to use Stirling's approximation, which is log of n factorial is approximately n log n. And we get this result for the change in entropy when we take a solute and stick it into a solvent. All right. Finally, and this is it, I promise. Finally, when we connect back to Gibbs free energy, the enthalpy, we're going to call this term right here U plus PV. Enthalpy is the heat of mixing. If we're assuming U, PV, and T are constant, therefore any change in Gibbs free energy is given by dg delta G is minus T delta S, and we rearrange all of this delta G in terms of the number of particles we have in solute and solvent, and we connect this to the chemical potential. dg is minus chemical potential of the solute, solvent times change in number of particles times plus the chemical potential of the solute, change in number of particles, plus VDP minus SDT, right? This we know. where the terms, these are in terms of the molar or molecular fractions given here. So, and the change in chemical potential of the solute and solvent may be written as change of the solute is kBT log its change in concentration. Change in the solvent is minus kBT times the change in the concentration in the solute over the concentration of the solvent. Typically, concentration of the solvent, you're not thinking of that as changing at all because there's a lot more of it than there is the solute, right? And that's one of the approximations built into this. All right, and that's it finally for this section. And when you get into the problems, it will be better, I promise. It will be much better. We'll see you there.